From our last lecture, now we can give the definition of a Laplace transform. Okay, so let me get my pen here. So suppose that we have some function f of t, okay, is a piecewise, and this is the key thing here, right? Is a piecewise continuous function. Okay, so suppose that we have some function f of t and it is classified as a piecewise continuous function, then the Laplace transform okay, of that function f of t is denoted we kind of use like a cursive L, the contents of the function here. That'll be our input, and defined as okay, so it will be defined in the following way. We have the cursive L, which is for Laplace transform, the input, which is the function that we're transforming, okay, and this is a piecewise continuous function, and this is equal to this integral from 0 to infinity, so it's an improper integral, and it's e to the minus st f of t dt. So let's take a moment and reflect on what this definition says. It says we have some exponential function e to the minus s times t. S would be a constant here. T is the variable that's changing. We are literally summing on the interval from 0 to infinity over this expression, this product between the function that we have and the exponential that's being multiplied into it. And it's this solution for this piecewise continuous function that will create what we call the Laplace transform. Okay? So there is an alternative notation for Laplace transforms that is also very popular. So again, let me grab my pen here. Okay. And for the sake of convenience, we can denote a Laplace transform as the following. We can also say capital L f of t, okay, is equal to capital F of s. Okay. Sometimes I'll use this notation, and I'll be sure to inform you when I do. And so with this alternative notation, we note that the transform is really a function of a new variable. In this case, the variable is s. And that all the variables of t will drop out in the integration process. Okay, that is the essential idea. So we're transforming the function from one variable into another, but the two will still essentially be equivalent to one another in various ways. Okay. So now, the integral in the definition of the transform is called an improper integral, and it would probably be best to recall how these kinds of integrals work before we actually jump into computing some of those transforms. And we're going to go ahead and jump into an example of that right now. So let me go ahead and give you guys an example to get your feet back into the groove of how to do an improper integration. Okay, so here's our first example. So we're going to evaluate the following integral. or I'll just say evaluate the integral. Okay, it's going to be the integral from 0 to infinity. It's going to be EC times t dt. So you might recognize that as, for example, e to the minus st, but instead minus s has been converted into c. And we're going to observe how this comes out in the integration. Okay, so here we go. First step, you need to remember how to convert improper integrals to limits. So the integral from 0 to infinity of e to the c times t dt, okay, and this is a blast from the past, this will be set equal to the limit as n goes to infinity, okay, and the integral from 0 to n, so you can see what happened here, right? We converted the integral into a limit, and it's still e to the c times t dt. And that's all there's to it. That's how you rewrite any improper integral out there these days. So now to do the integral, we have to evaluate that limit. So let's go ahead and do so. With this in mind, we can observe that the right-hand side then looks like the following. It will be the limit as n goes to infinity, okay? And the integral of e to the ct, well, that's going to be 1 over c, using the chain rule here. And then it's e to the ct, okay? And then the interval we were looking at was from 0 to n, right? So we can then evaluate this further and show that the limit as n goes to infinity becomes 1 over c e to the c times n, right? So plugging this in, and then subtracting it from 1 over c. When we plug in 0, this e to the ct becomes 1, so we're left with 1 over c, and close parentheses. So at this point now, we have to be careful. The value of c will influence our answer, and we've already assumed that the value of c was non-zero, okay? But now we need to worry about the sign of c. If c was positive, the exponential will go on to infinity. On the other hand, if c is negative, the exponential will go to 0, correct? So the integral is only convergent. In other words, the limit exists and is finite, which is necessary for Laplace transforms, provided that c is less than 0. So in this case, we're going to say the integral from 0 to infinity, which was our original improper integral of e to the ct dt, okay, is going to equal minus 1 over c, provided, okay, provided that c is less than 0, okay? So when we evaluate these improper integrals, it is important in the context of Laplace transforms, we have them to be convergent. So again, I'll reemphasize, if c was positive and non-zero, the limit would not have been convergent, it would have been divergent, and it would not have provided the answer we need, especially for a Laplace transform. Okay, so that's the solution for that. So let's go ahead and actually compute a Laplace transform. All right, so let's go ahead and jump to a new page, and let's look at a new example here. And we'll do this example in the next video. Stay tuned.